Hi, I will present the project 1, where we analyzed the probability distribution of rolling 5 platonic dice. Where we analyze the probability distribution of rolling 5 platonic dice, calculate the probability of winning a game based on this distribution, and validate our results using Monte Carlo simulations. So for task 1, we calculated the exact probability distribution of the sum of 5 platonic dices, these 5 dices. Yeah, and we used NP array to define the probability distribution for each die. And then we used convolve, this function convolve, to define the probability distribution for each die. Each die has an equal chance of landing on any face. And after that, we calculated the possible sums from 5 to 50 with a range. And when we run this, we will get the list of probabilities from 5 to 50. Yeah. In test 2, we calculated the probability of winning the game. You win if the sum is less or equal to 10, or if the sum is higher than or equal to 45. The probability of winning is approximately 1%, so it's not high at all. In task 3, we used Monte Carlo simulation to estimate the probability of winning by running 1000 trials. We used np.random gradient on each one to simulate each die, simulating rolling each die 1000 times. And after that, we calculate the sum of the dice for each trial and add them together, sum of rolls here. And then we had the condition that I talked about earlier. Sum is less than or equal to 10, or sum is higher than or equal to 45. And then we get the wins. And we divide that by trials to estimate the probability of winning. And when we run this program, we see that it's approximately 1% or 0.01. And if we run it again, we can see that it's approximately, now it's 1%, but it's approximately 1%. If we run it again, okay, there's approximately 2%, but usually it's approximately 1%, as you can see. Wait, wrong one. Yeah, approximately 1%. For task 4, I forgot to show this. This is from task 1. So when we put in the list in a graph like this, we can see that it's moves up. The probability increases and then decreases when the sum go to 50. Yeah. So for task 4, we explored how to estimate the probability of winning, converse as the number of trials increase here. As the number of trials increase, as the trial size increase, The probability stabilizes around 1.07% here, as you can see. The higher the number, stabilize to that. In task 5, we used this formula to determine that 100 trials are needed to keep the relative error below 10% when comparing the Monte Carlo estimate to the exact probability. So to summarize, we computed the exact probability of winning using convolution and validated it through Monte Carlo simulations. The winning probability is around 1.07%, and 100 trials are sufficient to maintain a relative error below 10%.